Okay, good morning, class. Welcome to our last science seminar for the semester. Semester's almost over. Yay or boo? Yay! Yay! All right, I think so. All right, so we saved the last for best, and because the last is so good, I'm not even good enough to introduce our guest speaker to you today. So we had to bring in the best introducer of the best seminar speaker today, and that is our own Dr. Curtis Wesley of the math department, and he is going to introduce us to our speaker. So let's give Dr. Wesley a warm welcome.
Thank you for the introduction. While I introduce our speaker. What can I say about my speaker? I've known him a long time, probably, he says about 14 or 15. I met him at Tex Prep, which was a summer program for middle school students and high school students. He was my first introduction to homeschool students, actually. He was a homeschool student. And I remember being in the logic class. We were teaching logic at the time. And him just, answering the questions. And he was really engaged. He was fully active. About a year and a half later, they contacted me to do some tutoring with him, right, to teach the math courses. So we started getting into math. He was doing regular algebra, I think algebra 2 at the time. And I noticed how excited he got when we were talking about math. And we would talk for hours, right? They paid me for 1 hour, but we would go 2 hours, 2.5 hours. His parents had to literally come and get him so that he could go home. And so we got this kind of relationship going. He decided he was going to do his degree in mathematics, undergraduate. Once he got out of undergraduate, he got hired immediately at a company called Armtech to do some statistics work. And now he went back and got his master's in statistics. And he just got that, he'll be graduating this May with his master's in statistics. So a really, really great guy. He's a part of our family. We just love him to death. So here's our speaker, Jonathan Adams.
Well, thank you. I was going to open with a joke about the best for last, but he saved me from being egotistical, so that works. Hopefully I'll live up to this. So as Curtis said, I have a bachelor's in mathematics and a master's in statistics come May. Is there any way to get this to go away? Yeah, I'll leave it. And, well, I'm basically here to talk to you today about some problems that I've come across and solved using mathematics in the crop insurance industry. When I first wanted to enter mathematics, I asked a lot of people, what can you use a degree in mathematics for? And it seemed like most of the answers were, there's a lot of stuff you can do. Great, what? Nobody would tell me. And I was afraid, well, all you can do with a math degree is teach. Fortunately, this is not true. At one point, when I first went into college, I contemplated going into engineering, and I was going to double major in mathematics. And one of the engineering advisors told me, nobody is ever going to hire you to solve math problems all day. That was a lie, and I'm very happy about that. So today what I'm going to talk to you about is 3 problems that I have come across at my work at Armtech, and how I went about solving them. I've sort of built it into 3 levels. The first one is a very basic problem. Don't really need a large mathematics background. The second one gets a little more complex, talks a little bit about time series. And then the third one is where I actually get into a little more theoretical results. There's some nice graphs to illustrate them. Anybody here had statistics, a course in probability? A handful? Okay, that might go over everybody's head, but I've tried to keep it very basic, and hopefully the graphs will help illustrate what I'm trying to cover. So first, I also want to say that I have not had a chance to time my presentation, but I will be keeping an eye on the clock. I may have to quickly brush over a couple of things, and feel free to ask questions. So, background. Well, what is crop insurance? Does anybody know?
It's when you insure your crops.
Yes. That's about all I knew when I went into crop insurance, too. It actually turns out that it is a partnership, a public-private partnership. It is headed by the USDA's Risk Management Agency. You have RMA, and you have AIPs. AIPs are approved insurance providers. So those are private companies that take the information from RMA, and they handle all of the actual policy maintenance, working of claims, marketing, collecting of premiums, cutting checks for claims, things like that. Whereas RMA, what they do is they do the actuarials under the hood. They design the products, they rate the products, they send all of the information to the AIPs, make sure the ARPs are charging the correct amount, paying the correct amount, all of that stuff. And RMA also performs reinsurance for the AIPs. Anybody know what reinsurance is? Reinsurance is basically insurance for insurance companies. As an insurance company, you say, I'm going to sell you this policy on your car, but they sell it to lots of people. If some big event happens and they are losing a lot of money, they want insurance themselves to try to tone that down so that they can cede some of that risk to others and make sure they aren't going to go over with a big, one big event. So RMA acts as a lot of stuff. They're actually a pretty interesting part of the government. Now, crop insurance companies, crop insurance policies cover a lot of different risks. 3 of the main ones are yield protection, so protection against the actual yield that you are going to be having in your for the given year. Revenue protection also guarantees against price drops in the commodities market. And then group risk protection, this is one where people are grouped by county. So if people in a county purchase group risk protection, they are all put into the same pool and they are paid claims based on how the county did as a whole. So in terms of the entire county's average revenue, the entire county's average yield, things like that. Let's see. Because it is a government program, all of the rates are the same. So if you purchase insurance from me for, what county am I in? I'm sorry? Greg County? Okay. So if you purchase insurance on 100 acres of cotton from my company in Greg County, that's the same as, you would pay the exact same amount as if you purchased it from any of the other 15 AIPs. It is all the same across the board. So basically what AIPs have to do is they have to entice business by selling their software pretty much. The software controls everything. It controls the actual policy maintenance, going in and inputting your information, changing anything, adding crops, taking crops off, reporting your acreage, all kinds of stuff like that. It's also what's used to handle all of your claims, generate any reports that anybody might want. So it's very vital to our business. We pretty much sell our software. Thus, we have to find a lot of ways to innovate our software. We want to be better than all of the other AIPs out there. So we want to find ways of automating it, speeding it up, making it look pretty, all kinds of stuff like this. Now, this is not just a job for computer developers. Fortunately, my boss knows this, which is why he hired me. He found a mathematician and he said, I know you can do a lot of cool stuff for us. So that's what I've been doing. So, this first problem was a problem they have been working on for quite some time. Let's see. Yes, an acreage report is a report that's really popular. Basically what we do is we take all of the fields that they are insuring and provide different information about it. So how many acres, what crop was planted, where it's located, various things like that. And we also provide them a little map that shows them a map of their field. Now, it's not uncommon for there to be lots of fields in a policy, and that can generate some really large reports. So what we wanted to do was we wanted to say, can we group these fields to where we have multiple fields per page, but group it in such a way that it looks visually appealing? Fields that are nearby are grouped together, fields that are distant are on different pages. Well, they had a couple of ways of doing this, but none of them ever really stuck. One of the basic ways they did it was just say, okay, what if we expand the field, see if anything's touching. If they touch, we put them on the same page. It was very rare that fields touched, so you would have 2, maybe 3 fields on a page. And so if you had, say, 800 fields, that was a huge report. So was there any way that we could take these fields and group them together in an optimal way and do it quickly? Now, I apologize, I do not actually have an image of these fields, a sample report, because the fields themselves are considered personally identifiable information, and I didn't want to go out and have to find any, take care of any of that. So you'll just sort of have to use your mind in terms of what the actual fields look like, but I do give an actual example, some sample data I generated. And before I actually show that data, notice this right here. The initial methods involved nearest neighbors. I'll be talking about that in just a second when I show the image. So these are not the fields themselves, these are just a sample of fields, and these only represent the centroids of the fields. So you have over here a large cluster of fields in the center. A lot of them are probably touching nearby, but since this is just the fields, since this is just the centroids, you only see dots. We have a small cluster here, here. So if I were grouping this via nearest neighbors, it's actually called k nearest neighbors. You have to have some value of k. You want to say, okay, choose this point, now give me the k nearest fields around that. Well, that would require some sort of optimal selection of k, and that doesn't really take into account a lot of, well, this field here is the nearest, but it's still halfway across the map. So here is a field, a cluster of what looks to be about 6 fields. If I did k nearest neighbors with k equals 4, choosing one of these, if I started with this field, I would grab these fields, but this one right here would have no place to go. So on the map, on the image, this one would probably be associated with the next 3 fields here. And that just doesn't look good, having one field here and then a bunch of fields way over here on a report. Not to mention, k nearest neighbors can take a little bit of computation time, which we wanted to cut down on. Is anybody here familiar with clustering? Anybody dealt with clustering before? Interesting. Anybody know what machine learning is? Okay, machine learning is sort of a field of algorithms that try to provide a way of optimizing your processes by automating them through a computer. Machine learning allows you to sometimes train an algorithm so that in the future it looks at data you've input, compares it to that set that you've already given it, and then outputs results. Clustering is a form of machine learning, and it's typically used for classification. Basically, you group like points together and you assume that the like ones have the same classification. You usually try to minimize some sort of distance calculation or dissimilarity calculation. What I'll be using today is just your standard Euclidean distance. K-means is a very popular and very fast unsupervised clustering algorithm. What that means by unsupervised is that you cluster the stuff, but you don't actually look at the classification when you're clustering it. You just cluster it based on the distance between everything, and then just assume everything in a cluster is classified as the same. It requires 2 inputs. Your desired number of clusters k, similar to your k nearest neighbors, and an initial set of cluster centroids. And the algorithm works as follows. You select your value k, choose your initial k centroids, calculate the distance of each data point to each centroid, assign each data point to the cluster that has the nearest centroid, then you update the centroids, you take those new clusters, find the centroid of each of those clusters, and then you iterate starting with step 3 until you finally have convergence, i.e. those cluster centers do not change. Now that's a lot to take in, so here's a quick visual example. I simulated 2 clusters of data, one cluster here, one cluster here, and I said take this and this as my initial cluster centroids. So these points right here were assigned to this cluster, these points right here were assigned to this cluster. You compute the centroids of each, and they get updated as such. So this moves here, this moves here. The second iteration, the new values are assigned as such, the centroids are updated, and you continue iterating until you see here we have our original data set clustered as it should be. So, how does that work when applying it to our problem? Well, hopefully you can see the colors fairly well here. Some of them start to blend in a little bit. I apologize, it was the best scheme I could come up with at the time. In my opinion, this looks pretty good. You have these fields are clustered together, none of them touching this. These are together, none of them touching this. This one's split up into multiple fields, which is perfectly fine given the inputs I started out with. These are grouped together, and basically, when I look at these actually look like decent clusterings. These look like something I might have come up with had I just looked at it and traced it out by hand. And this was all done automatically. I didn't tell the computer anything. I didn't even give it an initial set of clusters. I had it randomly generate some. Now, because I had it randomly generate some, there's actually a way to improve this. I won't really talk about that too much, but I have come up with a way of simulating a decent set of initial clusters, and the results become even better. For instance, you see a tiny cluster right here, and then another cluster right there. typically my results would have both of those combined. So this is a way of quickly calculating clusters, throwing them onto a report, and it works beautifully. It works fast as we would want. We haven't really had any complaints about people saying, oh, this looks ugly, anything like that. It actually cut down one of our 160 plus page reports down to 30 pages. That was impressive in my opinion. So I'm curious, can anybody catch the error in using this method? Well, remember I said it's a clustering algorithm, and clustering is typically for classification. I've not actually performed classification here. All I've done was use clustering to group stuff nearby. I don't care about classifying it. They're all fields. They could all be corn, they could be corn, soybeans, wheat, they could be anything. I don't care if I grouped corn, soybeans, and wheat here or anything like that. So this is one thing that I wanted to point out today. One thing you will be noticing me do is using a lot of algorithms for purposes that they are not necessarily advertised for, one of them being this. People say clustering is for classification. You don't have to use it for classification. One thing I hope you'll gather today is that what you are learning in your math class is a tool set. It is then up to you to figure out how to adapt that tool set to whatever. So just because the theory says one thing, you could very well find a use for it somewhere else. So that brings me to my second point, which requires, again, a little more background. Anybody familiar with precision agriculture? Anybody here know much about farming? Let's put it that way. Okay, this is clearly not West Texas. Somebody raised their hand on precision agriculture. Who was that? What is precision agriculture?
They use GPS to plant the crops in such a way, and they adjust the number of crops per acre based on previous year's results and the soil fertility.
Yes, pretty much. That is a small amount of precision ag, but you said the key, which was precision ag involves a lot of GPS data. What they do is they slap a really powerful, really accurate GPS onto their tractor, and then as they're driving through the field, they are constantly collecting data, geotagged. So maybe every 2 or 3 seconds, they collect a point. And they say, okay, my yield at this point was blah, the temperature was this, the soil moisture was this, my seed rate was this. They collect lots and lots of data. And it's actually a fairly new field, so people are still trying to figure out ways of how can we analyze this data, how can we get useful information from this data. There are huge areas open for research in this area. It is fascinating. There's actually various organizations, not organizations, I don't know what they're called, but there's basically a group that meets annually to try to define the basics of precision agriculture. Because right now there's a lot of systems, but they each are designed by a different company, which thus has their own system of doing things. For instance, C++ or coding languages, they all have a base set of rules. If you code C++ as such and you use a compiler for C++, it will work. Whereas right now, if you try to mix precision agriculture information across systems, it's going to break on you because they just aren't built using the same standard. A couple of systems are FarmSight by John Deere and Trimble by Trimble Agriculture. I won't really talk too much about those. Actually, I won't talk at all about those other than this. As I said, the measurements are geotagged, and then FarmWorks is a software that it's created by a private company, and they provide their software so that people, farmers who don't necessarily have a statistics or an analysis background, can still generate a lot of really nice reports. They have heat maps that they can provide to them that show different calculations at different spots of the field. They can perform different statistics on it. They can do all kinds of stuff, all kinds of analysis inside this software. And typically the goal of analyzing all this data is to optimize the farm. Maybe you don't want to spend the money applying nitrogen to the entire field. Maybe you've looked at your heat map and you notice, oh, there's only this one patch of red somewhere in the center of this field. I'll target my nitrogen there and I'll leave everything else the same because it's doing really well. One problem that we came across was we wanted to know when is a field irrigated and when is it not? Can we determine this based on the actual point data that we are given? Now this one here, this is an actual report. This is not one of our reports. I scraped this off of Wikipedia because that means it's public. And yes, I did cite it. That's in my work, cited. So basically what you see here, this I believe is a heat map of soybeans yield. So as the farmer was collecting his soybeans, he had his precision ag system on his tractor, and as he was harvesting all of that, it was calculating how many bushels per acre at each of these different points. Here you can see a little legend of what each of these colors represents. So red is between 5 and 35 bushels per acre, orange is 35 to 42, etc., etc. So it gives a really nice way of showing just how your field looks. And in the future, he might be able to say, okay, these areas that are red, how did they differ from these areas that are green? Can I adjust something next year? Maybe I need to add better drainage here, or maybe I need to irrigate better, provide more nitrogen, anything. So it allows them a way of trying to analyze and better their fields for the next year. This is simulated data because, again, I didn't want to show any actual data since that's private, so you will never see something this nice in our data. But it is decent enough to give you an idea of what's going on here. So what this is a simulated field with an irrigation pivot in the center. Anybody know what an irrigation pivot is? A couple? Okay, so for those who don't know, you basically have this well right here at the center, and you have a long row of hoses. And they just go in a circle. They move once every 30 seconds to a minute, and it irrigates the entire field. It takes a long time, but it works really well. So basically the irrigation pivot would be hitting this area, but it would be missing this area. So if this were yield, we would expect to see something like this. In the center, you would have much higher yields than you would here around the edges. This is a simulation of non-irrigated data. You can see that it looks a lot like noise. There isn't really any pattern here, but you still see that there's a lot of red and green patches. What we wanted to do was figure out a way to smooth this data, but we had to do it in such a way that for here, this data was the same because it shows us a lot of information, whereas whenever we came across this, we could smooth it. Now, if we were doing this by hand, that's pretty easy. You say, oh, this is clearly noise, let me smooth that. This is clearly irrigation, let me leave that alone. But we needed to figure out a way to optimize this. Could the computer decide when to smooth and when not to smooth? Well, how might we go about solving something like this? Any ideas? Yes?
Having it notice greater differences in certain areas, because the irrigated one had a lot more green in one spot and a lot more red in another spot, and the one that looked like noise, there weren't like locations that had huge differences between them.
Okay, that's possible. So basically what he said was we would assume that a lot of these points that are together have a very similar value. A lot of these points have a higher difference, whereas over here, they should, for the most part, be the same. The difference between these points is fairly minuscule. It's quite possible. Any other ideas?
Use that cluster form.
We could try clustering. I'd have to think about that for a little bit, but we could definitely try something like that. Are you talking about like trying to cluster the image to where this is in a cluster and the other pieces, or?
Just to separate the green from the red.
Okay, we could try clustering. That's possible. Let's see. Well, what if we think about it this way? What makes the irrigated different from the non-irrigated? Well, there's some sort of break there. I think he touched on it where he said there's probably some sort of difference between the irrigated and non-irrigated portions. Think about it this way. How is a field typically planted? What would you do if you were planting a field? You're doing it in rows. So most likely if you're planting a field, let's look at this one, you are going down and up, and you're basically going back and forth the whole time throughout. If we think about it this way, this could be thought of, this data could be seen as a time series, because there are times associated with each of those data points. So we could say, okay, well what if we look at the data, if we plot it based on time? Is there any sort of alternating pattern? Does the noise look like noise? Well, here is an example of irrigated data. Notice how it tends to oscillate a little bit. It also, there's different breaks where you see this sort of invisible line here where it shifts in some areas and shifts down in some areas and shifts up in some areas, but overall you see this nice little pattern here. And then you also have a few outliers. These red lines were basically just something I came up with to try to trim the data. This is an example of the non-irrigated data. I don't really see those oscillations here. These basically just look like chunks of noise. So we need to try to find a way of separating these. Is there any way, any form of, is there any function that whenever we plug all of this data in, it gives us some sort of, this is noise, this is not noise? Well, anybody familiar with white noise? A couple of you. White noise is basically, as it says, noise that is uncorrelated. If you were to plot the if you were to calculate the correlation between points at different lags, so the correlation of points that are five lags apart, they would be 0. Any lags apart would pretty much be 0. There are lots of tests for white noise, so is it possible to adapt one of these tests to this problem? Because this looks like it might be white noise in my opinion. Well, I went through, did a lot of digging, and I found one method proposed by Lobato and Velasco, and it focuses on the periodicity of a time series. That sounds like what I want. So a little bit of background on this. The autocovariance function at lag k, gamma k, is just your definition of your covariance. This is expected value for anybody who has not had statistics yet. You can also write the autocovariance based on this function f of lambda. This is called the spectral density function. I won't go too much into this, just know that the spectral density function typically is a way of trying to rewrite a covariance in terms of periodicity. This function here, the periodogram, I think is how you call it, again is a way of trying to get information on the periodicity of that function. And finally, this quantity here that you can't really see, it's just a constant, n minus 1 over 2. So, a hypothesis test, which probably won't mean a lot to most of you here since you haven't had statistics, is pretty much just a way of saying, here is what I want to test, now let me find a way of testing it. Basically what we want to say is, we are assuming that our data is white noise. This gamma k equals 0 means that the covariance between data points at all lags is 0. That is our definition of, that is a property of white noise. If the covariance between all of our data points at these lags is 0, then we probably have white noise. This is as opposed to there is some lag such that our covariance is not 0, i.e. there is some lag somewhere where there's a non-zero covariance, thus there is some sort of correlation in our data and we do not have white noise. Now, that this can be, we can test this by working with this equation here, 2 pi f of lambda, where f of lambda is our spectral density function, over the initial covariance. I believe this winds up being just the variance of the data. Variance at lag 0, so the variance of the data with itself, pretty much. This test statistic is what was derived. Right here, this is the sample estimate of this value right here. And it was shown by Lobato and Velasco that it converges in distribution to a normal 0,4 when thrown in this form. Now, in this form, basically what this means is that we can then test our original hypothesis. We have a way of calculating values for which we can reject. We can calculate our rejection regions. So then we plug our data in, we calculate this, and we say, okay, the value was this, our rejection region was here, so either the data is white noise or the data is not white noise. Anybody here had experience with hypothesis tests? Okay, a little more than I expected. How can I... A hypothesis test is really just a way of saying, here is my data, does it satisfy what I want to show? Don't worry too much about this. This is a theoretical result, which that is all I'm going to talk about there. Our data, when I tried using this with this here, it turns out that this is not actually white noise. It fails this test every single time I run it. But that doesn't mean this test is useless. The test itself, using this result, isn't useful to me, but this test statistic is very useful to me, because who says I can't just create a custom rejection region? Why can't I look at my data and see what are the values for those that I want to smooth? What are the values for those that I don't want to smooth? Is there some number that I can calculate so I can test it on my own? There's absolutely nothing saying I can't do that, and that's exactly what I did. So this is a histogram of those test statistics. What I did was I took a set of fields and I calculated that test statistic, and then I also classified, should this be smoothed or should I leave it the same? The bluish tint is fields that I should smooth. The peach color is values that I shouldn't smooth. I should just leave them alone. And as you see, those that should be smooth are over here. They have really small values of that test statistic. Values that didn't need to be smoothed were much higher. And actually, you'll see that there's a few values that I said shouldn't be smoothed over here. After I looked at it again, I realized, oh, I was basically finding patterns that didn't exist in this data. Maybe there was a small patch of green somewhere in the field, so I assumed, let's leave it alone. But actually, that was just a random patch. So I did some more adjusting and found that, okay, a value somewhere in this area should be used as my rejection region, and then I could easily code it. Every time we had a field, all you do is you calculate that value and say, is that value less than that rejection value I calculated? If it is, smooth it. If it's not, leave it alone. And I never had to look at it again. So any questions on that? No? Did I completely lose everybody with that? If I did, there might not be much hope. There might not be any hope for this next section, which I apologize. So what is this next section? Cat modeling. Not quite that cat, though, fortunately. CAT modeling is actually short for catastrophe modeling, and this is a big deal in the insurance industry. This is something that has been around for the past couple of decades, but it has become even more relevant as of late, especially because of what happened in 2008 with the housing bubble. Let's see, do I talk about that here? I do not. I will talk about that in a minute. So what is catastrophe modeling? It is essentially a throw it against the wall and see what sticks approach to risk management. You look at your data and you say, I would expect this to affect my results. I would expect this to affect my results. And then you go from there and say, how are these correlated? How could I model all of this stuff? If you can have a pretty decent model for what you would expect in the industry, then you can start simulating lots of events and saying what happened in those simulated events. Therefore, you don't actually have to be in the insurance industry 10,000 years. You just have to have a pretty decent model, and then you simulate 10,000 years of events in that insurance industry and say what happened, what was the likelihood of things happening. You can assign probabilities to events without actually having to have a specific model for all of those events, because from a frequentist standpoint, probabilities are assigned based on how often they occur. Well, if you've never had the event that you're terrified of happening occur, you can't assign a probability to it from a frequentist standpoint. So basically, you simulate it and say, how often is that going to happen? Somebody here knows what I'm talking about. Let's see. And yes, they provide CAT models provide a really nice way of allowing leaders of a company to make decisions, because now they have a little bit more information regarding what they fear. So if you're purchasing reinsurance and you're trying to decide how much reinsurance do I want to purchase, you can say, okay, well, I would expect us to lose this much money this often as opposed to this much money this often, and then they can adjust their reinsurance values from there. So catastrophe models involve focusing on the correlations, typically the worst case events. These worst case events are usually referred to as the tails. I'll show you the tails in a minute when I actually show you what I'm about to talk about. An example of these tails, basically what the tail is it's how does the data correlate when things get really bad. If the data isn't very correlated, you want to model it as such. But if the data is correlated, you really need to model it as such, because if the data is correlated when things get really bad, that could mean that your events are going to get worse than you thought. And that is exactly one of the reasons why we had the housing bubble. When the bankers, when their analysts were modeling everything, they said, okay, well, if this person here is foreclosed on, that doesn't mean there is no correlation between this foreclosure and any of the houses surrounding that being foreclosed on. What they found out was when things get really bad, if this person is foreclosed on, it's very likely that this person is going to be foreclosed on, and this person, and it just took off really fast. So those models that they had, they told them nothing about what happened in 2008 because they did not focus enough on the tails. Now, the best way of actually modeling these tails is with a multivariate distribution. Since most people here have not had statistics, I'll just tell you, multivariate distributions are ugly to work with for many reasons. Well, yeah, they're ugly. That's the biggest reason. Second, they are impossible to visualize beyond two variables because you need multiple dimensions that we just cannot actually view. Second, multivariate distributions are much less common than single-variate distributions. I can't tell you many off the top of my head. The only one I can name off the top of my head is a multivariate normal. And I will tell you this, you should almost never use a normal distribution. It just will not work in real data for the most part. There are exceptions when you start talking about asymptotics and things like that, but in my opinion, it is used way too often. Finally, goodness of fit for higher order distributions is also a lot harder, especially since you can't visualize it. You have to rely on test statistics and information that you calculate based on various functions and tests and things like that. So, multivariate distributions, very hard to work with. Let's give a quick background. CDF is your cumulative distribution function. Most of you probably don't know what that is, but I won't bother going into it right now. I'm running a little low on time. But basically, there is this theorem that if you have a CDF, fx of x, and you set a random variable y equal to those outputs, then that random variable y is uniformly distributed on 0 to 1. Now, we also have this definition of a marginal probability density function. If you have random variables x1 through xn that have this joint PDF, then the marginal for xi is the integral over all of the remaining variables of that PDF. And finally, a copula. A copula is a multivariate distribution function defined on the unit cube 0, 1 to the nth power, or not to the nth power, but the unit cube in the nth dimension with uniformly distributed marginals. This copula is very powerful. It is the heart of catastrophe modeling due to Sklar's theorem. This right here, for anybody who doesn't know, is basically the representation of a multivariate distribution. What Sklar's theorem says is that if we have a multivariate distribution, there exists some copula C such that the two will be equal. So basically all we have to do is fit marginals to each of our values on their own and then find the corresponding copula that would have given us this underlying distribution function. Copulas basically take values and they control the dependence structure of all of the data. So marginals are really easy to fit because those are typically just one dimension, and we can visualize that. We can find stuff like that all the time. Then all we have to do is find some sort of dependence that simulates what we're seeing. So that is a lot of information that's probably confusing. Let's illustrate it with graphs. Here are 4 different copulas. This is the Gaussian or normal copula. All of these were simulated to have a Kendall's tau correlation of 0.75. Each of them is 1,000 observations. So the Gaussian copula typically gives you a linear simulation, and it's symmetric. Notice here how the data is a little more spread out at the corners. This is because for what is known as tail dependence, i.e. how correlated the data is when it gets to the tails, for the Gaussian, it has 0 tail dependence. Once you get to the tails, the correlation structure does not change with this model. This is another reason for the housing bubble. Everybody was using the normal, the Gaussian copula. There was no tail dependence in their models. As opposed to the T copula, which does have tail dependence. You'll notice that these are a little tighter over here. As you get to the tails, the correlation becomes stronger. A Clayton copula, it has tail dependence at the left tail, but pretty much none at the right tail. The opposite is the Gumbel copula. No tail dependence on the left, but a lot of tail dependence on the right. Yes?
What are the axes again?
The axes, these are just uniform variables. If you were to plot the marginals of U1, you would see that it's uniformly distributed, and same way for U2. This is really just The reason you use uniforms is it works out nice and it can easily be transformed into whatever the underlying distribution is due to the probability integral transform. So let's take a couple of example marginals. This is a gamma 2, 1. This is a beta 4, 2 distribution. How would you simulate, or due to copulas, we can simulate observations from these two distributions that have some sort of correlation that we pre-specify. So basically what I did was I decided, let's take this Clayton copula, which has a correlation of 0.75, and assume we have data from this distribution and data from this distribution. Let's simulate an observation from that. And this is what we get. You'll see here, remember the Clayton copula, it has a tight tail at the left, no tail at the right. You see that with this data. As you go to the left, your data starts to get much more closely correlated with each other, and then it starts to spread out as you get to the right. Notice here, this is our gamma distribution. This is the marginal of that data. So we've paired up all of our observations, but we also make sure that we follow those marginals. This is the gamma marginal, this is the beta marginal. It might look a little backwards to you, but that's because it starts at 0 and goes to the top, so it still has that right hump over here. This is very powerful. Because we have a way of simulating stuff like this, we then have a way of trying to build into our model much more complex events than we would get from, say, linear regression or some of the simple modeling that you're probably interested in or familiar with. This, I tried building this with linear regression in the very beginning. I learned very fast you do not want to do that. It will not give you useful results. So how do we use catastrophe models? Well, basically what I've done, I will not go into the actual model itself, but at my company I have built us a catastrophe model for some of our projects. And this is one type of report that we are interested in. What this is this is the spread of all of the different results. These are loss ratios. I've taken off the values on the axis just to protect our data. But this was one type of product, this was another type of product, and this was how our results varied when they were combined. And basically, the x-axis is the probability in years. How often is this event going to happen? So this is a 1 in 5 year event, 1 in 50 year event, 1 in 250 year event, things like that. So it's much easier to see what happened, how often was it going to happen. So, I think I'm just in time. What do I hope you have gotten from looking at these things? Well, first, as I said earlier, somebody told me nobody will actually pay you to solve problems. That is wrong, because everything I showed you here is a math problem. It may not be directly out of a textbook, but if it were directly out of a textbook, I would get bored really fast. And so far, I've never been bored at my job in the 3 years I've been there. Algorithms in theory have their place. They're nice to have. I use them to make sure that what I'm using is not going to break something profoundly. Once I've made sure of that, I don't care anymore. I say, how can I adapt this for my problem at hand? And I run with it. So yes, you do have to worry about the algorithms in theory and what it's used for in class, but once you get out of class, you're free to do with what you want. You should be trying to use it in different ways. That's the only way you are going to innovate. That's why your degree is a tool set. It is just a way of problem solving, and it is up to you to figure out how to use that problem solving when you get out into the real world. Also, Google and Stack Overflow are your friends. I have used them so much to figure out different methods of doing stuff. Stack Overflow will tell you how to code it, will probably even give you certain algorithms. Google will give you all kinds of resources that are great. I know a lot of universities typically encourage using article databases when you do research. Those have their place. I've used them occasionally. I actually found an article that verified my catastrophe model was correct because I found somebody doing something similar. But other than that, I don't really use them very much. A lot of times you will find articles on people's personal websites, university websites, things like that. And in closing, I want to give a slight bit of advice, because a lot of you, I imagine, are planning on going into the workforce. Even if you go into academia, this is still useful. When you finally get your first job, enter it with a yes attitude. And I don't mean to sound like some person who is yes I can type thing. I do not mean to sound like a motivational speaker. But this is what I did when I started my job. I said, if somebody asks me to do something, I'm not going to say, we'll see, or I'm not going to say, I'm not sure if I can do that. I'm going to say, it will be done. And the amount of stuff I have made myself do is pretty amazing. 3 years ago, I would have never seen myself building a model that could output stuff like this. I have literally started from scratch 9 months ago, and now I am readying to present this model to my boss next week. So, say yes when asked to do stuff.
Yes. And let's say yes to answer questions from the audience. Do we have questions from the audience today?
Yes.
For the slide that had the 4 different copula on it, were those all generated from the same set of data, or
They were
from
just
different-
randomly simulated. These are just random observations. There was no underlying data. The only thing underlying was the fact that I said I want it to come from a model that has Kendall's tau correlation of 0.75. That's it. Any other questions? I hope I haven't confused you too much. And I hope I've given you something useful to think about.
So have you predicted the next real estate bubble or whatever bubble that might be?
I have not, because I'm not doing real estate. My main interest is what would be the next catastrophic drought, which I'm still working on.
Okay. All right. Okay. Well, our speaker will be here for a few minutes. You have questions here. Otherwise, we'll be in the Joyce Room of the Corner Cafe. If you want to join us there for lunch. And if you don't have a lunch planned, Dr. Fraser is kind enough to buy you lunch today. So come on out to the Joyce Room and join us all for lunch over there. Let's thank our speaker very much.